So two quick example problems, one for a confined aquifer situation, one for an unconfined aquifer situation, to look at flow of groundwater in the subsurface. So consider a confined aquifer 33 meters thick, 7 kilometers wide, and there's two observation wells located 1.2 kilometers apart in the direction of the flow. The head in the first well is 97.5 meters. The head in the second well is 89.0 meters. And K, the hydraulic conductivity, is 1.2 meters per day. What is the total daily flow through the aquifer? So we're going to write our equation that says Q prime is equal to K B dH dL. We've got 1.2 meters per day times our thickness, 33 meters, times dH dL. So we're going to have 97.5 minus 89 divided by the distance, 1,200 meters, 1.2 kilometers, and that equals 0.281 meters squared per day. And that's the flow per unit width. So Q is equal to Q prime times my width, which was 7 kilometers or 7,000 meters. So 0.281 times 7,000, and I get 2,000 meters cubed per day. Okay, so quite simple, plug and chug. Next problem. Consider this situation. So we have this dam or this berm that's separating two bodies of water. The one on the left has a depth of 20 feet. The one on the right has a depth of 2 feet. And you can see through that porous material, you can see the dotted water surface. Essentially, this is serving like flow in an unconfined aquifer, where the flow is going this direction. And we want to know, we're given the hydraulic conductivity is 10 to the minus first centimeters per second. We want to know what is the flow rate into the lower channel from the upper one in gallons per day. Okay, so our equation says Q prime is equal to 1/2 K H1 squared minus H2 squared divided by L. But our K is in centimeters per second. Everything else in this is in feet. And in the end, we want it in gallons per day. So what I want is I'm going to convert my hydraulic conductivity, which is right now in centimeters per second, into a strange unit, which is gallons per minute foot squared. And that's going to make it easy to just plug in this equation. So we're going to take K, 10 to the minus first centimeters per second. We're going to multiply by 60 seconds in 1 minute. We're going to multiply by 1 inch is 2.54 centimeters. 1 foot has 12 inches. And there's 7.48 gallons per cubic foot. Okay. So in the end, I'm going to wind up with 1.47 gallons per minute foot squared. Okay, this foot up here is going to cancel one of these down here, and I still have my minutes and my gallons over here. Okay, so now when I plug into this equation, Q prime equals 1/2 K 1.47 gallons per minute foot squared, and then multiply by H1, which is 20 feet squared, minus H2, which is 2 feet squared. Divide that by 30 feet, which is my length of travel here through the unconfined aquifer or the porous material. I'm going to wind up with 9.70, and again it's going to be, I'm just multiplying this whole thing on the right hand side is I have foot squared divided by feet, so it's just a feet, and I multiply that by this 1.47 gallons per minute foot squared, so I get gallons. I'm going to write it like this: gallons per minute per foot. Okay. Now I need to multiply by the thickness into the page, so Q is equal to 9.70 GPM per foot multiplied by 30 feet back into the page, and I get 291 gallons per minute. And then I just need to multiply by the number of minutes in a day, multiply by 1440 min per day, and I get 419,100 gallons per day. Okay, so fairly straightforward. I wanted to pick this one to just highlight the fact that the hydraulic conductivity can come in many different units, and often hydraulic conductivities are given in metric units, and but most of our groundwater calculations are in US units, and so there's frequently a conversion that needs to be made at some point, either between the hydraulic conductivity or later the transmissivity into US units.